Hello, my name is Melika Destani. I'm from Pattern Recognition Lab of Electrical and Electronic Circuits of Ferdowsi University of Mashhad. Today I'm going to be talking about boost converters, and you can visit the document using this link. Boost converters or step-up converters step up the voltage and step down the current, meaning that they increase the voltage and decrease the current. So, a principle of its operation is it stores energy using the inductor and the capacitor and then releases this energy through the load that we have and finally steps up the voltage. So, here we see a simple schematic of it using Python SchemeDraw library. It consists of an inductor, a diode, a switch, which could also be a MOSFET, a battery, and capacitor, and a resistor, a load resistor. So the way this works is when we close the switch, all the current, most of the current actually, flows through the switch here, and a little amount of current flows through the diode. So what happens here is the battery charges our inductor, and so the magnetic field increases in the inductor, and the polarity of it will be positive on the left side and negative on the right side. And from the relation we have from inductors, we can write the delta of the current equals to the input voltage, which is E, times the time that the switch is on, and then it's divided by the inductor's inductance. And when we open the switch, here we see another schematic of it when the switch is going to be opened. When we open the switch, what happens is that the magnetic field of this inductor drops, and the current, and this happens because our current is decreasing. Why is our current decreasing? Because we've opened the switch and the current isn't flowing from the switch anymore, and it is flowing from the diode. So our current decreases, and then since our inductor is resisting this, it starts acting as a battery, as a voltage source. So the polarity of it changes. It would be negative on the left side and positive on the right side. So our battery and our inductor will be in series with each other, and so the current that flows through the diode, or to be exact, the voltage that is across the capacitor, is linearly increasing, since it is now equal to the voltage of the inductor plus the voltage of the battery. And so on, we can say that the load's voltage, the voltage across the load, is also increasing because the voltage across the load in the off state equals the voltage across the capacitor, and we can say kind of equals the voltage of here. So the thing that happens is when we turn off the switch, our inductor is getting charged, and then the sum of our battery's voltage and our inductor's voltage will all charge the capacitor, and then the capacitor will start decharging using the load. And so we can see that the voltage across the load will increase, since it is now equal to the voltage of the capacitor, which equals to our E plus the voltage of our inductor. So in this state, we can also write delta IL, and we can again use the relation we have for an inductor's current and voltage. So it will equal to our output voltage, which is our load's voltage, minus our input voltage, which is our E, divided by L, and times the time the switch is turned off. And we can also rewrite this using the duty cycle. The duty cycle is T, the time that the switch is turned on, divided by the cycle of this. So it will be T on divided by T on plus T off. So what is the purpose of the diode? The diode's purpose is it prevents the flow of current in the opposite direction. So when our capacitor is charging, why is it not discharging this way? Because the diode will be reverse biased, and then current will not flow through it. and the capacitor will only discharge itself using the um, load we have here, this resistor. So here we have derived the relationship of the rippling current, the delta IL we spoke of, and during the TIA on, we use KVL in here. When the switch is turned on, well, we can see that via our voltage of the inductor equals E. So then we use the relationship of the voltage and inductor, voltage and current in inductors, and we write this equation, and then we integrate it from the minimum current we have until the maximum current we have. So it will be from the beginning until we turn off the switch. So so our rippling current will be like this. This is written with frequency. We can also rewrite this using our cycle. So the average output of the voltage, we can use KVL during the off session of it. So it will be this part. When it's off, we will write a KVL in this. When we write this, we derive this via our load's voltage will be the battery minus our output voltage, or the voltage that is across the load. Again, we rewrite this using the relationship we have for the inductor, and we integrate it from a maximum to a minimum I. We can see here how our current goes from a minimum to maximum, and then again. So we use these bounds for our integration, and after simplifying it, we derive the relationship of our output. So we see here that our output voltage equals our input voltage divided by 1 minus duty cycle. So this we can see is always a value less than 1, since our duty cycle is always between 0 and 1. And when we subtract it from 1, it is still between 0 and 1, and so our output voltage increases, and as we said, boost converters step up the voltage. And to see if the current actually decreases, we can say that this conversion is a lossless conversion, so our input power equals our output power. So our initial current equals our output current, and so our initial voltage is the batteries, and our output, we've derived the relation here, and we can see that our output current decreases um, and it step downs. So we see how that happens. If we want to increase the output voltage and efficiency, well, we can always increase the inductor's value. We see in these relationships that the inductor's value has an influence on it. And we can also increase the current rate. So if we want to increase the current rate, we use, instead of a mechanical switch we can use MOSFETs, like as we said, transistors, and in this way we can increase our output voltage. So we have some losses in this circuit, as every circuit has. We have conduction losses, switching losses, diode reverse recovery losses, and magnetic core losses, also capacitor losses. Its applications are wide and are in a wide range. So they're in power supplies, LED lighting, and solar power systems, also in electric bicycles and telecommunications and sensor systems. In conclusion, we can say boost converters play a critical role in modern electrical engineering by providing efficient solutions for stepping up voltage levels in wide range of applications. We have reached the end of this documentation. I hope this has helped you. Thank you for watching.